Hello and good morning. You're probably excited because this is the last bit of material for the school year. This is on electrode potential. I'm going to run through it. It's probably going to take 12 to 15 minutes. It's not going to be hit very heavily at all on the test or the final. But I almost forgot about our joke of the day. If you're not part of the solution, you're part of the precipitate. Get it? If you're not part of the solution, you're part of the problem usually, but yeah, it's chemistry. So that might be the last joke of the year. They're getting very thin, as you can see. All right. Today we'll be learning about electrode potential. So before, when we were looking at these electrochemical cells, we said that we could put a voltmeter in here. It's basically a machine that can measure how much electricity is going through here. So scientists can figure out exactly how much energy can go through there. And they can use that for practical purposes, such as in batteries. And by now, hopefully you know that these galvanic or voltaic cells are really just batteries. And there are a lot of different versions of batteries. Everybody uses batteries all day long. So it's essentially, how can we figure out what the electrode potential is? And more importantly, as far as this goes, whether the reaction will be spontaneous or not. In other words, does it require a battery or will it act like a battery? So it's essentially the measure and difference in what we call potential energy. And again, that's measured in a voltmeter between one half reaction and another. Determines the tendency of a reaction to occur spontaneously. The reaction that the others are compared to, because we have to have a baseline, or the reference half reaction, is this one. This is an electric potential of 0 because it doesn't happen spontaneously. I'm going to show you this a couple of times probably. It says see chart N in the yellow reference table. While I did not give you chart N, I will post one that looks like chart N, but I do want to show you that here's the same thing, essentially, on page 166 of your CRT, your Regents review book. So which one are they talking about? They're talking about H plus to H2. So that's why that is 0. Okay? That's why it's 0. And these are all called reduction potentials. I have a cleaner version of that I will post. And it's a little bit more extensive. And it looks like that. So we could look all of these up. Let's find hydrogen. So this is saying that hydrogen ions, if given electrons, will not spontaneously make hydrogen gas. That's why this is 0. Okay? All right, let's get back to it. At the top of the chart, we see that there's the strongest reduction reaction. In other words, it's the strongest oxidizing agent. And that would be F2. So I'll show you on this one again, because this one does have F2. That means fluorine gas, if given electrons, is going to form fluorine ions. That's the top. At the bottom is the strongest oxidation reaction. That would be the strongest reducing agent. So on this chart at the very bottom, you can see lithium. If it picks up an electron, it's going to be negative 3.05. Now let's see what these positives and negatives mean. Positive value means that there will be a spontaneous reaction. The reduction half reaction will be higher on chart N. So here we go. These are set up essentially the same way, but be careful. This is going to show the positives on the top and negatives on the bottom. In your Regents Review book, it shows the negatives on the top and the positives on the bottom. So be conscious of that. But the bottom line is, if you have a positive value, that means that there will be a spontaneous reaction. The negative value means it will not occur spontaneously. You need an electric current. In other words, this has to be driven by some sort of battery, or you've got to plug it into the wall. So what does that mean as far as this chart goes? That means this happens spontaneously. So do all of these up to here. That means lead all the way down to lithium will not go through this particular reaction unless it's hooked up to a battery or some sort of energy source. Okay? And now we can figure out, here's the equation, we can figure out what the electrode potential is, and we'll do a couple practices. So let's look. If we took magnesium and chlorine gas to form magnesium chloride, here's how we would figure it out. Would this happen spontaneously or not? Let's look. So chlorine, you know, is 0. It will pick up 2 electrons to form chlorine ions. So this is a reduction. Since it's gaining these 2 electrons, this is a reduction reaction. So let's look it up in this chart. Let's find chlorine. .36. Okay, it's shown here. This is where it is on my sheet here. So I would put a positive 1.36, and that V stands for volts. Magnesium. Will magnesium lose electrons spontaneously? Remember, this is an oxidation reaction because the electrons are lost. And if I look it up on my chart, negative 2.37, which is here. So now what do I do with these figures? I plug them into this particular equation right here. So E of the cell is 1.36, which came from this. I subtract it, and I keep my charge here. So positive 1.36 minus a negative 2.37 ends up, remember, keep change, positive, positive. This ends up being a positive 3.73. So if I put magnesium solid in with chlorine gas, this will happen spontaneously. Why? Because there is a positive, this ends up being a positive number. Okay? And again, the positive number means this is going to be a spontaneous reaction. Okay? This shouldn't be too bad. So let's run through these two. Switch colors here. Zinc, copper makes zinc copper. It's actually zinc cupride. So let's look up each of these reactions. First thing I'm going to do is look up zinc. Well, is zinc more likely? Let's look over here. Let's put copper and zinc. Is zinc more likely to get oxidized compared to copper? Well, where's zinc? Here's zinc, and here's copper. So zinc is the one that's going to get oxidized. Remember, it's most active. Copper is the thing that's going to get reduced. So if I start with copper here, it's going to gain electrons to form copper 2+. And you know by now that that's 2 electrons that are going to do that. So the zinc must be getting reduced. So this is the oxidized part. So I'm not going to start with zinc 0. I'm going to start with zinc 2+. Zinc only makes 2+ here. And it is going to, I made a mistake here. Can you see it? I made this oxidation, which it isn't. It is going to, according to what we just saw, this is going to get reduced. So I wrote that wrong. So that's reduced. Zinc, since it's above copper, is more likely to get oxidized. So the zinc is going to get oxidized by losing electrons. So I'm faltering here a little bit. I apologize. This is going to be 2+. That's the ion, gains the electrons. My apologies. These ions will gain the electrons to form the solid metal. And the zinc here is going to be solid. It's going to lose electrons to form zinc 2+. And it's going to lose 2 electrons. All right, sorry for messing that up a little bit. So, zinc is more likely to get oxidized, and copper gets reduced. All right, so what does that mean in terms of this goes? So, I'm going to write my equation again, switch colors. So, I'm going to put E0 for the cell equals E for reduction minus E for oxidation. E for the cell, which is getting reduced, it's going to be the copper. So I'm going to look up what the reduction potential of this reaction is. So copper 2+ is going to be 0.34. 2+ plus 2 electrons, 0.34. 0.34 volts. I'm going to subtract what's getting oxidized, which is the zinc. Let's look up zinc. That's a negative 0.76. Now, even though the confusing part might be, even though these reactions are shown both as reductions, it does not matter. You keep that because they've already changed the sign. Okay, that negative means it's not going to happen that way. It's more likely to happen that way. That's why it's negative. Okay, so it's negative 0.76. Negative 0.76 volts. Okay, so my final answer here is keep change, change, positive, positive, and that's going to be a positive 1.10 volts. So, is this spontaneous or not? This is spontaneous because there is a positive number here. Okay, so this will happen automatically. All right, last one very quickly. Spontaneous, we've got nickel and iodine making nickel iodide. This is a positive 2, this is a negative 1. So what's more likely to get oxidized? As you can see here, just from what I've written here, nickel is going to get oxidized by losing those electrons to form nickel +2. And the iodine gas is going to get reduced by gaining 2 electrons and then forming 2 iodide ions. Okay, so we've got 2 electrons, 2 electrons. So we could do a balanced reaction with it as well. So since this is losing electrons, this is getting oxidized. Since this is gaining electrons, this is getting reduced. So let's punch it in. E of the cell equals reduction minus oxidation. E of the cell equals reduction, which is I2. I'm going to look that one up on my chart. And it is here, 0.53. It's positive. And the oxidation of nickel is here. That's a negative 0.25. Answer. Keep change. That's change positive. That's going to be 0.78 volts. Therefore, it is positive, and that means this one will also be spontaneous. Okay? That's it. This is the rest of the material for the year. Your homework I will post. It's going to be the very last page of your packet. It's similar to the one you did for homework last night, but it aren't as many questions. Okay? Good luck.